Hello friends, welcome to another lecture of EMT. So today this is the topic of discussion, reflection and refraction of EM wave. So here is the question that we're gonna answer in this video that discuss the reflection and refraction of electromagnetic waves at the plane of interface between two dielectrics. Under what condition will the incident wave be totally internally reflected? Okay, that's what we're gonna answer. So first, before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And this is my Insta ID OJHALAKHYAJIT123. So you can follow me on Insta as well, right? So now let's start. First, let us take this is the interface between two dielectric medium. So this is suppose medium 1, this is suppose medium 1, and this is suppose medium 2, and so here is the normal. Suppose let me take this is the normal, and let me choose another color. Okay, so here is the incident wave. Suppose this is the incident wave. Okay, let me take this is the incident, just give me a second. This is the incident wave, suppose, right? And this is refracted wave, and this is the reflected wave. Let me take that way. This is the refracted, and this is the reflected, and this is the incident ray. Okay, so here you see this is this x-axis represents the interface between the two dielectric medium. Okay, and okay, let me write here incident wave, then this one is refracted wave, then this one is reflected wave. Now we know that angle of incidence is equal to angle of reflection, so that's why if we consider this is angle theta, suppose theta 1, let me take this as theta 1, then we can consider this one also theta 1, because according to laws of reflection, we know that angle of incidence is equal to angle of reflection, and the angle of refraction is suppose theta 2, let it be theta 2. Okay, so now you see, let me write what I have considered here first. So now let us consider two dielectric media 1 and 2 separated by a boundary plane, that is y equal to 0. So if the plane is on x-axis, that must be y equal to 0, right? Equation of x-axis is y equal to 0, and here you see that means if this is y-axis, then the boundary the plane separating this two media must be a yz plane, right? Okay, and that will be given by y equal to 0. Hope you have understood this. So then here you see, let epsilon 1 comma epsilon 2 and epsilon 1 and mu 1, then epsilon 2 and mu 2 represent the dielectric permittivity and magnetic permeability of medium 1 and 2 respectively. Okay, so then let us also consider that E1, E1 dash and E2 respectively be the electric fields associated with the incident electromagnetic wave that is traveling in the medium 1, okay, and incident obliquely on the interface between the medium 1 and 2, comma, then reflected wave which is reflected back to the medium 1, and the refracted wave in the medium 2. Okay, so let us also consider the angle of incidence. We know that the angle of incidence is equal to angle of reflection, so that's why you see angle of incident is equal to angle of reflection, that let both of them is equal to suppose theta 1, and angle of refraction is suppose theta 2. So here you see in this diagram, let it be theta 1, this is theta 1, both angle of reflection and angle of incidence theta 1. Okay, we have considered that way. I hope you have understood this. So here the electric field associated with the incident wave is E1 we have considered, and the reflected wave is suppose E dash, and the electric field associated with the refracted wave is E2. Okay, this is E1, this is E1 dash. Okay, the reflected wave is E1 dash, we have taken that way. So hope you have understood this. Now let me take a new slide, just pause the video and note it. Okay, these three electric fields, E1, E1 dash and E2 dash. So here E1 is the electric field associated with this incident wave. So direction of the electric field will be perpendicular to the direction of propagation. This is the propagation constant K1, suppose propagation vector of the wave, and this is the propagation vector K1 dash, and direction of the electric field must be perpendicular to this direction of propagation, and like this. Okay, so this is E1 electric field, and E1 dash is the reflected electric field associated with the reflected wave, and E2 dash E2 is the electric field associated with the refracted wave, right? So here it is, suppose its propagation vector is K2, suppose, right? So let me explain the diagram again, just wait. So here you see this is the incident ray, and this is the refracted ray, and this is the reflected ray, and here this is the x-axis represented by y equal to 0. Here is the surface that divides the two medium, let me take that way, and this is the incident wave, and propagation vector is K1, and the electric field associated with is in this direction. This is the electric field associated with this vector, with this incident wave, and the electric field associated here, let me take this is theta 1, and angle of incident is equal to angle of reflection, so that must be also theta 1, and here you see, just wait, and the electric field associated with this, that must be also perpendicular to this vector, right? And this is the propagation vector K1 dash, and this is the electric field associated with E1 dash, right? And this is the reflected wave, and this is the refracted wave or transmitted wave, you can say, and this is the angle of refraction, let it be theta 2, and this is the constant propagation vector here K2, and the electric field associated with this is this one, suppose E2, right? Let me take that way. So now you see, so if we split this into two components, here you see this is angle theta 1, so this angle must be also theta 1, this angle, this one must be also theta 1. If this angle is theta 1, then this is E1 cos theta, this component is E1 cos theta, and this is E1 sin theta. Similarly, if we split this one into two components, this one and this one, and this is theta 1, so this angle must be also theta 1, this one, just give me a second. Okay, this angle must be also theta 1, right? This is theta 1. If this is theta 1, then this is E1 cos E1 dash cos theta 1, and this must be, this angle is sine theta 1, E dash sine theta 1. Okay, E dash 1 sine theta 1, right? Hope you have understood this. Similarly, we can split this one into two components. If this is theta, then this must be also theta, this is theta 2, so then this must be also theta 2. So this component will be e2 cos theta 2. Similarly, this one will be sine theta, sine component, right? And similarly, you see, just wait, let me clean these things. Similarly, you see, just give me a second. Okay. Similarly, let me show you something else. See, this is the propagation vector here. This one is k1 dash. We have taken k1 dash, and it's this propagation vector is k2. So we can resolve this also in vector form, right? This way, and this one will be resolved into these two components. Okay, if this is the direction of propagation, right? Okay. If this angle is theta 1, this angle must be also theta 1, and if this is theta 1, this component is k1 dash cos theta, and this must be k1 dash sin theta 1 actually. Okay, and here you see this angle, not this one. If this is theta 1, then this angle must be also theta 1. If this is theta 1, then this one is k1 cos theta 1, and this is k1 sin theta 1. And similarly, this can be also resolved into two components. If this is theta 2, so this must be also theta 2. If that is the case, this is k2 cos theta 2, and this component is k2 sin theta 2. So from here we can say these three components are equal, right? You can see the vectors, this one, and this one. We can write k1 sin theta 1 is equal to k1 dash sin theta 1 is equal to k2 sin theta 2. These three are equal. So hope you have understood this. These three electric fields, E1, E1 dash and E2 dash, those can be expressed in this way. Let me go take a new slide here. So E1, this E1 electric field, that gonna be expressed by E01, which represents the amplitude, right? Exponential, or we can write e to the power I k1 dot r vector minus omega 1 into t, right? And E1 dash E01 dash e to the power, so this will be I into k1 dash dot r vector, right, minus omega 1 dash into t. And similarly E2 vector, that's gonna be E02, then small e to the power I k2 dot r minus omega 2 dash into t. That's how we can write. Okay, hope you have understood this. So just give me a second. Okay, what we can do here, let these electric fields, this electric field means those electric fields that we have mentioned here, E1, E1 dash, E2 dash, right, can be expressed by those equations, okay, that I have written below. So hope you have understood this. Now you see let me take this as equation number 1 suppose, and this is equation number 2, and this is equation number 3. So here you see this E01 here, this E01, then E01 dash, this E01 dash, right, E01 dash, let me use this ink, and E02 dash, sorry, not dash, E02, okay, where these are, you know, nothing but field amplitudes independent of space and time. Of space and time, right? And here you see, and one more thing, this may be complex. Okay, complex, right? So instead of writing maybe, if we write complex amplitudes, that will be better, because you know, when you get a real number, that can be also written in this form, complex form, right? So instead of writing maybe, let me write here just complex field amplitudes, okay, are complex. So let me write here complex, okay. Now you see, also let me mention K1 dash and K2 dash, K1 vector, K1 dash and K2 dash. What are those? Okay, these are propagation vectors. Okay, these are propagation vectors, right? Vectors associated with the you know, incident, reflected and refracted waves respectively. Right? So hope you have understood this. Just okay, let me write these things here. Okay. Now you see here, actually frequency, you know, this frequency doesn't change on reflection and refraction. On reflection and refraction. So we can write omega 1 dash is equal to you know, omega 2. Okay, these three are equal, so let each of them suppose omega. Okay, let us say omega. And you see here, this, if this is the electromagnetic wave, then if this is the direction of electric field, then magnetic field must be perpendicular to the electric field. But let me take this is the electric field, suppose this is the direction of electric field. Okay, because this, if this is the direction of the let me take k1, this is the vector direction of the vector instead of uh, and then just wait, let me show you here. This is the direction of the wave. Okay, then the direction of oscillation of this electric field, that should be perpendicular to the propagation of the direction of propagation of the wave actually. So let me take that way. Okay, then the direction of the electric field, this E1 dash should be in this direction. Okay, that perpendicular to this. So instead of writing this as E, let me write here K1 dash. This is the this propagation constantly represent the direction of the wave. So and similarly here also, this is gonna be the direction of E2, electric field E2, and this is the direction of K2, right? So now you see, so then let me show you something here. Here you see, so this is the boundary suppose, and this is the incident wave. So this is K1. Now you see, this is the if this is the electric field which is perpendicular to this, and this angle is suppose theta1, then this must be also theta1, right? This must be also theta1, and because you see, if you complete this triangle, now you see this is 90 normal, so this must be 90 minus theta 1, right? 90 minus theta 1, and this is 90. Okay, this is 90. So then this angle must be theta 1. Okay, then only the sum of these three angles of the triangle must be 180. And if this is theta 1, this is also theta 1, alternate interior angles, right? So hope you have understood this. So now, okay, now you see, if this is the electric field, so it can be resolved into two components. This is E cos theta, right? And this is E sin theta, E sin theta, right? So here this component will be the this will be the tangential component which is parallel to this boundary, and similarly here you see this angle this is E1 dash, right? This is E1 dash, here it is E1. Okay, this is E1 dash, and this is also theta 1, so it here this must be also theta 1, this angle must be also theta 1, and this component is E1 dash cos theta. So this is E1 cos theta, E1 dash cos theta. So and this is the refracted one, and this is the electric field. Suppose if that is the electric field, this angle is, if this is theta 2, then this angle must be also theta 2, and if that is the case, this must be E2. If this is E2, then E2 cos theta. Okay, so that's why we can write, now you see these two are opposite, so what we can write E1 cos theta 1 minus E1 dash cos theta, that's gonna be equal to E2 cos theta 2. So here this should be theta 1, right? So now let me clean this. Okay, so hope you have understood this. Now you see, let me write here something just with applying boundary conditions. I have made a separate video, on boundary conditions. Link is in the description box. You may go through. Okay. Now you see, if this is the case, and in this equation, you see, and as this omega 1 dash and omega 2, so this is supposed to be omega 2, not omega 2 dash, so just let me, so these are equal at the after reflection, right? And you see here, this condition that we have got, this must be satisfied, at all the points in the on the boundary, okay, that at the interface here, okay. So if that is the case, we can say that this power on exponents, this exponential part must be same, right? Okay. So here we can write that as we can write this condition has to be satisfied. This condition has to be satisfied at all the points in the boundary at all the time. So let me continue from here. Therefore, we can write k dot k1 dot r vector must be equal to k2 dot k1 dash dot r, right, is equal to then k2 dot r vector is the position vector, right? So then you see here, you see, this will be possible if k1 dash and k2 are coplanar, okay. Therefore we can write k1 comma k2 and k1 dash and k2 are coplanar. That means are on the same plane, okay. So these are you can say coplanar, right? Now you see, okay, now this k1 and k1 dash, so let me go back to the previous slide. Here you see these two, k1 and k1 dash, are on the same medium, that is medium 1, right? So that's why we can say that since let me take a new slide, okay. Since k1 and k1 dash are in the same medium, are in the same medium, that is medium 1, right? Okay, same medium, hence you see, okay, just give me a second. Before writing this, let me write one more thing. Now you see, let me draw the diagram again here. this is the y-axis, this is the boundary, or okay, this is the interface. Now you see this is the incident wave here. This in this direction we have k1 vector, here it is k1 dash, right, k1 dash vector, k1 dash vector, and this is k2, right, k2 vector. Okay, now you see if this is theta 1, then if we can resolve this, then here you see this angle must be theta 1, alternating to your angles if this is theta 1. Okay, and then this component is k1 sine theta. So if we resolve it into two components, if this is theta 1, so because angle of incidence equal to angle of reflection, so both theta 1, so then this component, this angle is also theta 1 corresponding angle. So now this component k1 dash sine theta. Okay, similarly we can resolve this also into two components. So if this is theta 2, this angle is theta 2, right, angle of refraction is theta 2, then just wait, let me write it clearly. This is the k2 suppose, then we can resolve this one. Here you see this is theta 2. If we resolve this into two components, okay, this is theta 2, so this must be also theta 2, and this component, this one is k2 sine theta 2. So this is, and this is, and this is. Now here you will see this three, those must be equal from this diagram, right? So here we can see, so from this diagram it is we can write that k1 sine theta 1 is equal to k1 dash sine theta 1 dash equal to k2 sine theta 2. So here this is simply theta 1, not theta 1 dash. Okay, k2 sine theta 2. So those are equal. And here you see, now let me cut this part. Okay, we don't need this. So this equation implies that you see sine theta 1 by sine theta 2, from these two you can write that k2 by k1. Okay, we can write that. Okay, k2 by k1, right? Okay, here we have considered that this is medium 1, this is medium 2, and here permeability and permittivity are epsilon 1 and the permittivity and permeability mu 1. Here we have taken epsilon 2 mu 2, right? That that's how we have considered, right, permittivity and permeability for these two mediums. Okay, now you see the propagation constant, this k, that is equal to omega root over epsilon mu. Okay, because you see speed of wave v is equal to omega by k, and v is also equal to 1 by root over epsilon mu. Okay, if we compare that, then using these two equations we can write this relation. Okay, so since we know that k is equal to omega root over epsilon into mu, therefore sine theta 1 by sine theta 2, instead of k2 we're going to write omega epsilon 2 mu 2 divided by omega root over epsilon 1 mu 1. So omega cancels, so we end up getting this only root over epsilon 2 mu 2 divided by root over, let me write under single root instead of writing that way, epsilon 1 mu 1. That's what we have got. So you see, and also speed of wave, that is omega by k, is also equal to 1 by root over epsilon mu. So that's why we can write this is equal to this is we can express this way, 1 by root over epsilon 1 mu 1 by root over epsilon 2 mu 2. If you simplify this, then again you're gonna get this, right? That's very simple. I have written this one here, written this one. Hope you know these things. These are very simple, simplification, just simplification. And this one is equal to speed of the wave in medium 1, and this one will represent speed of the wave in medium 2, right? Because you see v is equal to speed of wave is equal to this, so v1 will be equal to this one and this one, right? Hope you have understood this. So that's why what we can do, let me write this one here, this is gonna be equal to v1 by v2, right? v1 by v2, where v1 is the speed of the wave in the medium 1, and v2 is the speed of the wave in the medium 2, right? So now let me take a new slide. So this is what we have got, sine theta 1 by sine theta 2. Now let me copy this and let me go to a new slide. Okay, so this is what we have got. Okay, now this can be written this way, that again c by v2, just do one thing, just multiply c with the both numerator and denominator, then you can write that c by v2 by c by v1, and c by v2, that will represent the refractive index of medium 2 n2, and c by v1 will represent the refractive index of medium 1. This is refractive index of medium 2, and this one is refractive index of medium 1, and this is nothing but if you simplify this cross multiplication, this is nothing but Snell's law. This is nothing but Snell's law, right, of refraction, right? So this is all about reflection and refraction of electromagnetic wave. You see, at the plane boundary of two dielectric medium, right? So that's all. Now let us discuss about the condition of total internal reflection, okay, at the boundary. So now you see here, let me draw the diagram here again. This is the diagram. Okay, so we have taken the refractive index of this medium is n2, and this is refractive index n1 of this medium 1. Okay, Now if n1 is greater than n2, right, that means this medium 1 is denser medium and medium 2 is rare medium. Okay, so in that case, now you see the angle of refraction. Okay, if medium 2 is rare medium, then this you see this refracted wave, so let me cut it, that must be that should be bent away, that should bent away from the normal, right? So that's why in that case the angle of refraction must be greater, right? Then theta 2 must be greater than theta 1, right? Then theta 2 must be greater than theta 1, right? That means angle of refraction must be equal to angle of incidence. So from Snell's law that we have got now, okay, let me, okay, so from Snell's law we can write sine theta 1 by sine theta 2 equal to n2 by n1, right? And here you see, if this theta 1 increases, then theta 2 also increases. Okay, then at a particular angle, suppose if theta 1 for theta 1 is equal to, suppose, theta c, the angle of refraction theta 2 becomes pi by 2, that is 90 degree, then theta c is called critical angle. Okay, then theta c is called critical angle. Okay, and beyond this angle, if theta 1 is, when theta 1 greater than theta c, okay, then the incident wave will be reflected. Okay, then EM wave will be reflected. Okay, then total internal reflection takes place, right? Now you see, when theta 1 is equal to theta c, that is critical angle, then theta 2 becomes pi by 2. Then in that case, this equation will imply that sine theta c divided by sine pi by 2, because when theta 1 is equal to theta c, then theta 2 is equal to pi by 2, so it's supposed to be pi by 2, then n2 by n1, and then we can write, sine pi by 2 is 1, so we can write sine theta c is equal to n2. Now you see, from Snell's law, that is this one. Now from this equation, what we can write, that sine theta 1, let's find sine theta, this is angle of reflection, is equal to sine theta 1 by n2 by n1, right? N2 by n1. So if theta 1 angle of incidence is greater than critical angle, then you see for greater value of theta, sine of theta will be greater, right? So that's why what we're gonna have here, this sine theta 1, you know, when theta 1 is greater than theta c, then sine theta 1 will be greater than sine theta c, and if that is the case, from here what we can write, that sine theta 1 will be greater than n2 by n1, right? So if that is the case, then what we can write, then we can write sine theta 2, this will be, you see, if sine theta 1 is greater than this one, then this must be greater than 1, okay? So this must be greater than 1, so sine theta 2 must be greater than 1. Now you see, so if you know, the greatest value of sine theta is 1, we know that, okay? So if that is the case, then this theta 2 must be imaginary, therefore this theta 2 must be imaginary, right? Because you see, because sine cannot be, value of sine, value of just wait, let me write here, theta 2 must be imaginary, because value of sine theta cannot be, value of sine theta 2 cannot be greater than 1 for any real value of theta 2, okay? If this is imaginary, that means if this is imaginary, so that's why what happens, you know, then if this angle of refraction is imaginary, then, and you know, when the angle of incidence is greater than critical angle, then there will be no refraction, that will be there will be total internal reflection, right? So hope you have understood this. That means the entire wave energy is reflected back to the same medium which is we used to call total internal reflection. Right, so hope you have understood this. So thank you for watching, see you in the next video.